Hey everyone, welcome back. We are starting chapter 2 today. And we're going to start off by talking about the average rate of change, and eventually we're going to get to the instantaneous rate of change, which is kind of the goal, and actually is what calculus is we're looking for that instantaneous, and it all kind of coincides. The best way to do this is let's talk about, first of all, that the average velocity is the change in distance, and that's a capital Greek letter D that looks like a triangle, called a delta, over the change in time. And we've seen this formula before. Same idea, except now we're changing distance with respect to time. And to keep our eyes open, let's go ahead and do an example here. A rock is launched vertically upward from the ground. And I'm not sure what that n is doing there. S of t is a position function, is equal to negative 16t squared plus 96t. And this is the position of the rock after it's launched vertically upward from the ground after t seconds. And we're going to find the average velocity between each pair of times. So we have between 1 second and 3 seconds. So that is going to be represented by this here. And that there you can see is not going to be the exact value, but we're going to get as close as we can. First of all, I need to evaluate S at 1. And let's see, negative 16 times 1 squared, which is just 1, of course, plus 96 times 1. And I'm getting 80. And S position vector at time 3 is going to be negative 16, 3 squared, plus 96 times 3. So we'll redo this, but instead we will have 3's. I'm getting 144 for that, which means our average velocity is going to be 144 minus 80 over 3 minus 1. Because it's 64 over 2, or this is 32. And they say position of the rock. They don't say unit. I can only assume that they are using meters, but I'm not going to guess. Typically, when we're doing science and things like that, it's always in meters. And so there's our average velocity in units per second. And next up, what we're going to do is we're going to have, let's say we want to decrease the time. And you can see that my pink curve is a lot closer to my orange curve, to the actual black curve that you see there. And let's go ahead and figure this out. Now, I already figured out S sub 1, which is 80, so I only need the S2. And so let's redo this, but now we have 2's in here. Oops. And I'm getting 128. So our average velocity is going to be now 128 minus 80. That's now 2 minus 1. That's going to give us 48, again, meters per second, which I presume it is, but they don't explicitly mention whether the unit is meters or not. All right. Now, the goal here is ideally to figure out the graph when it touches at exactly one spot. And that is going to be instantaneous velocity, and that is our goal. So the blue line, the blue tangent curve is what that's called. Tangent is the Greek word for to touch. Versus the other lines, the orange and the pink, which actually are what we call secant lines. So A line joining two points on a curve is called a secant line. So once again, the orange and the pink that you see above there are the secant line. And again, we're going to have a different variation of the same formula. The slope of the secant line is going to be S of B minus S of A divided by B minus A. So again, it's all variations on the exact same formula that you see up there with the y sub 2 minus y sub 1 and so on. All right. So our goal, as I mentioned before, is to figure out the slope of the line that touches at exactly that one spot. That's not as good as my other one. Let's try again. That's going to have to do. And so we're looking for the slope of that line. And the way we're going to figure that out is we're going to use something called a limit. And this is going to be as the time is approaching 1 second. This is going to be S of t minus S of 1 over t minus 1. Now, what this means is we are jamming our time interval in both sides to exactly 1. Now, the problem is if t equals 1, if you look at my formula, that means I'm dividing by 0, and that's a problem. So we're going to have to figure out what exactly is that going to mean as we're getting closer and closer and closer to that. And we're going to do that with an example. So here we have a function, f of x equals 1 over x plus 2. Find the average rate of change of f of x over the interval 10, 10 plus h. And our answer will be in terms of h. So let's, first of all, figure out f of 10. No problem. Over f of 10 plus h becomes 1 over 10 plus h plus 2, or 1 over h plus 12. So our tangent here is going to be the limit as t approaches we're going to hold off on that. So we'll come back to that. Sorry, I'm jumping ahead. So the average velocity, or the secant slope, or whatever we want to call it, is going to be 1 over h plus 12 plus 1 over 12 over 10 plus h. This is minus 10. And I'm going to note that to subtract these two fractions of the numerator, I'm going to need a common denominator. So overall, this is going to equal, this is going to be 12 minus h plus 12 over 12 times h plus 12 all over, and I'm going to notice that minus 10 and 10 are gone. So this is just all over h. Now I realize this has become quite algebra heavy here. And up in the numerator of the numerator, that's going to be 12 minus h minus 12 over 12 times h plus 12 over h. And we end up with negative h over 12 times h plus 12 over h. And what's really nice about this is that these h's actually reduce out. And believe it or not, this is the actual function that we are looking for. Now, at this point, we have no idea why we're doing what we're doing, and that's okay. Ideally, at the very end, we're going to take h, we're going to say, h, you go to 0. And you'll notice up until we got all the way to here, we would be dividing by 0 because we have all over h, all over h, all over h. Until they reduce out, then we're going to be able to shove that to 0. And h is the, let me go back to here. H is that step size. So if I'm here, my first h was a distance of 2, meaning from 1 to 3. My second h was just from here to here. That's a distance of 1. Ideally, we're going a distance of h. And we're going to take h and hopefully shove it down to 0. That's ultimately the goal. And we can't do that until we reduce out that extra h, which we have done. All right, so we have a graph here. And it says the graph of f of x is shown below. Estimate and list the value of x where f of x has a horizontal tangent. Now remember, tangent is a line that crosses the graph at exactly 1 point. So I want to point out that one such line is there, where we're touching it at 1 point. Another such line is here, again, where we're touching at exactly 1 point. So those are our horizontal tangents. And you can see the x values are going to be -4 and 6. And let me just make sure we understand where I'm getting that from, -4 and 6. And that is our introduction to our functions and instantaneous velocity. More to come here in just a minute when we get to the next video. Thank you.